So we're going to show off the progress on BattleZips V2. It's about 2 weeks away from completion, but we wanted to make a quick progress report. Essentially, we have all of the shot working, all of the shot circuit working, unit tested, and we have the valid case for the board circuit working, as well as we have like one of these working, but we're playing around with getting this to be as concise as possible. Essentially, it's throwing a bunch of extra errors that we don't necessarily want to be showing. So we're just trying to make sure it's as clean and descript as possible and going through all this. But it seems to be performing as expected. So we can go take a look at that. For the board first, we've got a valid board configuration, second valid board configuration, and I guess we have, this isn't, okay, it's not even, so yeah, we just don't have the other ones. So we'll just run this. So this takes a board configuration, hashes it, and then synthesizes a zero knowledge proof that this is a valid board configuration, essentially. And then that this board commitment, which is publicly exported, is the hash of this board commitment as it's transposed according to the logic in the placement chip and the transpose chip. So as we can see, this worked for two different placements. So again, we'll go through and check the rest of it, but in general, it appears to be working. And then the shot circuit, we have all of it working for. We'll go a little more in depth. Essentially, we've got cases for, so I guess really quickly how the shot circuit works is that we don't check that the board is the same. We would do that at like the smart contract level, or we would use like some sort of accumulator outside of these specific chips in the state channel. So it just takes in any board, essentially. And then it also takes in a shot commitment, which has a single bit flipped, which corresponds to the shot that you want to hit. And it basically checks whether or not it hits, whether or not on a given row there's a bit flipped for both the board and the shot. And then you publicly assert to the shot, the hit, and the public commitment. And that assertion of the public commitment is how you link it back on the smart contract level. But once we have hashed it, taken all the public inputs, and synthesized the circuit, it will basically say, yes, for this board commitment you gave, this shot commitment, which is clearly can be decoded as X is 3 and Y is 5, produces a hit. Or I guess, yeah, in this case it produces a hit. And in the other case, it produces a miss. So these show what we expect, and then we also want to see what happens when we try to trick the circuit. So the very first case, what happens when we try to say, since the way that Halo 2 works is that it's all field elements. It's all integers on a prime field, finite field. We need to constrain the value to be 0 or 1, so we check what happens if we pass in a value that's not 0 or 1, and it handles that. We check a pretty basic case that is really fundamental. What happens if you try to lie and say that you hit when you actually miss? And this will produce an error. And then something that's probably not going to happen, but we still want to check for, is you assert that it misses, or sorry, I guess since it's reactive, you probably wouldn't do this one very much, but you would do this one. You would lie this way. So we check that you can't lie this way, but you can't lie either way. You have to assert the correct way. It checks to make sure that you actually are making a shot. So if you pass in a commitment that has no shot, it's going to fail. if you try to pass in a commitment that has multiple bits flipped, essentially making multiple shots, it's also going to fail. As well as on top of that, we wanted to show on top of that, like if you if you hit multiple times, there's a second issue, and we weren't able to throw like it throws some of the same errors, but we wanted to demonstrate that there's that second layer as well of verification to make sure that you're only producing a single hit. But that also it's going to assert the same, like that hit number is either 0 or 1. It's counted, so it technically could be 2. So you could say that you could pass in a hit assertion of like 6, which is not a boolean, and then you could hit 6 times and it could count 6, and this would all check out, except for the fact that it's a multi-shot, as well as the hit count is more than 0 or 1. So that's most of the like core game logic, as well as just some zero knowledge security stuff. Essentially, this is probably the main thing. The others are kind of redundant, but this is basically you want to make sure that the publicly asserted board, like if you're trying to pass in a different hash than you're actually calculate, or a different board, I guess, then you're actually calculating in the zero knowledge proof, it will basically get angry. It'll say that this hash is not the same one as expected. So that way we can make sure that when we do, either from some sort of accumulator circuit or from the smart contract, inject the board commitment, it does lock up. Otherwise, if you're trying to, or I guess in that case it doesn't, it works. Otherwise, it will lock up. So I guess I don't want to ramble on too much. So these are all the same. Basically just checks that your what is computed internally and what is passed in externally is the same. So I guess in this case, so invalid hash, you would be internally asserting the wrong hash, and then here you would be externally asserting the wrong hash. And then you can assert the wrong shot commitment and the wrong hit assertion as well. So just to run those all, there we go.